microscopic experiments and studies by X-ray diffraction have all shown that the intact enzyme looks like this. In order to be able to correlate local and gross conformational changes in ATCase, we need to look at the structure in a little bit greater detail. We have already seen that there are two catalytic subunits held together by three regulatory subunits, but now what I want to show is that each of the catalytic subunits is a trimer of three polypeptide chains, and each of the regulatory subunits is a dimer composed of two polypeptide chains, and there is a space in between filled by water in the intact molecule. Thus, we have a protein in which there are 6 catalytic chains and 6 regulatory chains organized as 2 trimers and 3 dimers. Now, what we would like to do is add a ligand, succinate, which is a competitive inhibitor for aspartate and binds at the active site in the inside of this molecule, and study some gross physical property of the molecule. For this, we chose the sedimentation coefficient because it is a measure of the overall volume and shape of the molecule. As we increase the concentration of succinate, you will notice that the sedimentation coefficient, which begins at 11.8 Svedbergs, gradually decreases to 11.4 Svedbergs and reaches a plateau at very high levels of succinate. This corresponds to a conversion of the molecule from the unliganded state, which would be the T state, to the liganded molecule and the swollen molecule in the form of the R state. Thus, as ligands are entering the molecule undergoes an isomerization from the T to R form and a decrease in the sedimentation coefficient. Having demonstrated the gross conformational change in ATCase caused by the addition of active site ligands, we would now like to proceed with much more detail, asking questions about local conformations. In order to do this, we will focus first on the catalytic chains and ask the question, if ligands bind to the C subunits, will there be an effect on the conformation of the R subunits? The second question is, if ligands bind to the R chains, will there be an effect on the conformation of the C chains? And finally, we would ask, if ligands bind to the upper C subunit, will there be an effect on the conformation of the lower C subunit? In order to answer these 3 questions, we must do some protein engineering. We start by adding mercurial and taking the enzyme apart into subunits. So we can then have free catalytic subunits and free regulatory subunits, which we can now alter chemically in any way we wish. We can put spectral probes on the regulatory subunits, or conversely, we can put spectral probes on the catalytic subunits and then reassemble the molecule in well-defined fashions so we know where the probes are. In this way, we have assembled a protein molecule in which the catalytic chains are colorless and a spectral probe has been incorporated into the regulatory chains. And now what we're going to do is add an active site ligand and see whether the color changes in the regulatory chains. As the ligand is added, the molecule swells, undergoing the conformational change measured by the sedimentation coefficient, and the color does change in the regulatory subunits. If we allow now the molecule in the R state to go back to the T state, we notice that the color returns once again to the original form. Thus, we have answered question 1 very clearly. Ligands which bind to the C chains cause a change in the conformation in the R chains. Now let us turn to the second question. Do ligands which bind to the regulatory chains affect the conformation of the catalytic chains? To answer this question, we have incorporated a spectral probe on each of the 6 catalytic chains on the ATCase molecule by nitrating a specific tyrosyl residue with tetranitromethane. In this way, we have made a molecule which is now colored in the visible, and therefore we can detect changes in that color as a consequence of adding either ATP or CTP to the regulatory chains. As you can readily see, CTP causes a color change in the catalytic chains, and similarly, ATP causes an opposite color change in the catalytic chains. Now let us look at that data quantitatively by actually measuring the absorption spectra with a spectrophotometer. If we plot the change in absorbance as a function of wavelength caused by CTP, we see a beautiful negative peak. Conversely, if we now add ATP to the solution and plot the change in absorbance, we see there is a positive peak. Thus, we have demonstrated that ATP causes an expansion of the molecule and an increase in absorption in the catalytic chains, and CTP, conversely, causes a contraction of the molecule and a decrease in absorption in the catalytic chains. Will ligands binding to one catalytic subunit affect the other catalytic subunit? To answer this question, we build another hybrid molecule. In this case, one subunit is active and native, and the other subunit has been specifically inactivated and also modified to contain a chromophore, the same nitrotyrosyl group that we'd used heretofore. Now when we add ligands to the bottom subunit, we can see whether there is a change in the absorbance at the top. When this experiment is done, and we follow the progress of the experiment, we notice that it is allosteric, and as ligands are binding to the bottom, the molecule swells, and moreover, there is a color change. We have converted it from the T state to the R state. If we allow now it to go back, we see the color changes once more as we convert it to the T state. And finally, once more, we'll go back to the R state and watch the color change as ligands are binding to the bottom and not to the top. Thus, we have demonstrated communication from the bottom subunit to the top subunit, mediated primarily, almost exclusively, by the regulatory subunits. Now we would like to look at that more quantitatively by actually looking at spectra. In order to do this, we will first look at the direct effect of taking a subunit which has been modified to include the same chromophore but not inactivated. Thus we can add ligands and watch them bind and measure the spectral change. And if you plot now the change in absorbance as a function of wavelength, you will see the difference spectra with a beautiful negative peak at around 450 nanometers. The direct effect, therefore, is to produce a decrease in absorbance when the ligands are bound to the chains containing the chromophore. Now let us look at the hybrid once again. We're going to bind ligands on the bottom and look for the communicated difference spectrum on the catalytic chains at the top. This will be the indirect effect, and we'll look at that spectrum very carefully. As you can readily see when you plot the change in absorbance, we're now getting, instead of a negative peak, we get a positive peak. In other words, the communication difference spectrum, due to crosstalk between the two subunits, is positive, whereas in the previous experiment, the direct effect gave you a negative peak. This molecule has been particularly useful, not only because it allows us to demonstrate crosstalk between the two subunits, but it also enables us to show that when the molecule is converted from the T state to the R state by active site ligands, we obtained a positive difference spectrum. And you will recall that we got the same positive difference spectrum when we used ATP to promote the conversion from the T state to the R state. And now we'll allow the molecule to go back to the T state, and we can see the color change. And once again, the color changes as we go to the R state and back to the T state. Thus, we have demonstrated that ligands which promote the conversion from the T state to the R state, regardless of whether they are binding to regulatory chains or to catalytic chains, cause the same spectral change in this inactive colored subunit. Having demonstrated crosstalk between the two subunits in this hybrid, we would like to ask one final question. Is the change in the spectrum intimately tied to the change in the swelling of the molecule, which is a reflection of the quaternary structure? In order to do this, we will use this hybrid once again, and we will add succinate, which will promote the swelling of the molecule and therefore the decrease in sedimentation coefficient. And we will measure that along with the change in the spectrum. And then we will go back to the T state once again, where the molecule goes back to the original form. We will now plot the percent change in the sedimentation coefficient as a function of succinate concentration. And as you can see, the change starts at 0 and rises to 100% as we add about 10 to the minus 2 molar succinate, with the midpoint being in the neighborhood of 10 to the minus 3 molar succinate. Now if we plot on the same scale the percent change in absorbance, we see that the set of points is almost exactly superimposed on the first set, with the result that a single curve fits both sets of data. In this way, we have demonstrated conclusively that the conversion of the molecule from the T state to the R state produces a change in the tertiary structure of the unliganded chains, and thus quaternary changes are intimately linked to tertiary changes. These physical, spectroscopic, and kinetic studies have demonstrated that there is a one-to-one correlation between the changes observed kinetically and the physical changes observed either by sedimentation or spectroscopic measurements. When the molecule goes from the low affinity state to the high affinity state, there is a swelling of the molecule, which we now call the transition from the T to the R state. This swelling is accompanied by a change in the tertiary structure the catalytic chains and the regulatory chains. Moreover, ligands which bind to the catalytic chains communicate their effect onto the regulatory chains and vice versa. And finally, there is crosstalk from one catalytic subunit to the other catalytic subunit. This represents an example of a concerted transition in which the molecules are affected throughout all of its polypeptide chains as the molecules swell from the T state to the R state.